Good morning, everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm an applications engineer here with EasyPower, and we very much appreciate your attending our webinar this morning. So the topic today is dynamic stability, and the focus is not on an exhaustive explanation of all the feature set. It's primarily focused on how to get up and running with one line or a change to your one line diagram that you can produce results that mean something and hopefully guide your use of the tool going forward. One of the things all CAD tools permits is the ability to implement a what if situation relatively quickly and inexpensively. And so that's kind of what I'm aiming for today. So welcome all. And as we are in the habit of doing, I'd like to start with a poll question, and it has to do with power flow. It turns out power flow is the basis for doing the dynamic stability, and we'll talk about that in a bit. So my poll question is, how often should a power flow analysis be conducted on an electrical system? Appreciate your feedback. Don't obviously, there's no obligation involved in this response. And ironically, there's not a right or wrong answer. It's not an absolute question. So I do appreciate your feedback. Your opinions count, and they will help me kind of focus where we talk about or what we talk about during this next 30 minutes. So it looks like we have a quorum here participating. I'll leave this open another 5 seconds to see if anybody missed it. And all right, so here's how people responded. And I mentioned it's not a right or wrong question, that this basically is, my suggestion is this is based on the policy and the health of the system, the policy of the facility owner or manager. There are times in the life of a facility where running a load flow is important because of problems or because of trending that is observed, or an instability in the system, and consequently you need to be on top of the load flow. There are times when the system is mature and there's no changes going on, and so you can do a load flow less frequently, and the idea there is to catch a trend or develop a trend in the early stages. And then obviously, and the time I think that most people engage in the load flow analysis is when we're expecting a change in the loading or a change in the configuration of the system. And in that case, I've actually talked to companies that did a lot of data logging because they had to substantiate the load on the load distribution, whereas they could minimize the data logging required if they had a more current and accurate load flow. So there's, again, this boils down to company policy. It's not a given answer and not a given policy or recommendation. Okay, so appreciate you participating, and let's get on with our discussion. So basically we're talking about load flow, which we want to understand the real power flow, the reactive current and power flow in the system, what the voltages and currents are at each of the buses, and the losses. And one of the elements that we want to stay on top of, frankly, usually in areas where there's a penalty from a utility company if we don't maintain a certain power factor, is to stay current on what's going on with our power factor and optimize on that result. Again, the EasyPower load flow module makes it relatively easy to do this, and one of the necessary adjustments, if you will, is tuning our load situation in the digital model that we've created, oftentimes from an arc flash need, but the same one-line model can be used for load flow if we can adjust the loading, the number of loads, the percentage of motor activity so that it matches what we're seeing from the utility or from our SCADA system. And again, because EasyPower is relatively easy to kind of interact with the analysis and turning systems on and off, it makes it relatively easy to do these what ifs. EasyPower uses a relatively new method of doing calculations called the current injection method. It's actually more robust, and especially for larger systems, much faster. And it allows it specifically in large systems for doing dynamic stability. It allows very quick solutions and quicker convergence of the calculations. One of the features that's built into load flow is what's referred to as transient motor start. And basically what that does is calculate the voltage and current impact on our system if during the time there's a locked rotor on our starting motors. And so frequently people will perform this as a worst case event, and most of the, well, because it doesn't include the reaction of the network to that particular start. All they're doing is a one-time calculation of the power flow with that one motor or that collection of motors locked with the locked rotor. It doesn't really give us a true picture of what's going on in the overall system. So that's where dynamic stability comes in. It actually calculates load flow equations every half cycle based upon some stimulus in the system and the reaction of the network, and consequently the re-reaction of our modified motor or generator or whatever's going on that we're trying to analyze. So what I'm going to do is compare those two. Well, and so where this comes into play is as I start the motor over time, it's going to recover from the locked rotor situation. And so how that impacts my system is relatively important, and it's not illustrated that well in just a power flow calculation. So what I'm going to do is compare transient motor start with dynamic stability doing a motor start, and then basically suggest that it's possible to tune my soft start controllers to minimize the impact of my motor start. So with that introduction, let's kind of jump into this admittedly simplified one line. But let's say I've got a one-line diagram here with some large motors, and I've already got some power factor correction on them. So in a normal power flow solution, I've got my power factor, which I'm illustrating here by the real power versus power factor on the utility. And so we're in the favorable range of 0.96, 0.97, but that's a function of the fact that we have load flow power factor correction capacitors on these large motors. So the question is, what happens when these motors lift off or start off? So I'm going to go to power flow, open up this particular motor itself, which is right now running at 100% power. At the initial solution, I'm going to start with 0% power, 0%, and then start the motor to see what the result is on my system. So I solve it. I can see that I have no motor current because this motor is not running. And by starting that one motor, I can see I have, at least for some period of time, albeit relatively quick, some significant losses and overcurrent situations and voltage drops on the near-term buses. Things are worse if I come back here and say, well, what happens if I start two motors? And so if I start this one at 0 and start it simultaneously, we can see I really have a problem, or potentially a problem, if those two light off at the same time. So this is a function of the power flow module. It's called impact motor start. So the question is, how can I isolate that, or how can I minimize that impact on the system when I've got to start these two motors, and let's say I have the ability or have built-in soft start capability. So let's kind of go back to our one-line diagram. Let's not save any changes on the loading, and then go into dynamic stability and see how this, just want to verify that my power flow is still at 100%. I'm going to go to dynamic stability. Well, to see a difference in dynamic stability, I have to add and this is kind of the trick, if you will. This is what this focus is about. I've opened up the motor data dialog box, and for short circuit, I just had to fill in these three tabs. For power flow, I have to fill in the information here. For impact motor starting, which is what we just did, these are the factors that influence there. For stability, though, we have to enable the motor model, which is a full flux model, and it's dependent upon the characteristics of the motor itself. Now, most of the time, it may or may not be able to get that data immediately, but what the tool allows me to do is load in generic information on a typical type of motor. So let's say this is a standard induction motor, 500 horsepower. I'm going to import that from the library, device library, and I can either overwrite with the power factor and efficiency or keep whatever I've set up in my one line. I'm going to go ahead and overwrite it now. And so now I have these parameters set up in the flux model that we're going to use in the simulation. For starting, I'm going to do the same thing here. For generic, let's use standard time versus speed. We'll calculate that out as a plot. And same thing for while it's running, time versus speed. Again, this is a gross approximation of how to get going, but I'm making the point. Now, what we're going to do when I get to it is I have these parameters in my model that are related to soft start and the time element that the soft start will be invoked. And so that's what we're going to come back and adjust. So for now, I'm going to take this motor, copy it, and paste over here to take all that information from my soft start. From my flux model. And as I did, you notice we get this icon that now includes a rotor type of element, indicating that there's some information in the soft start, in the flux model for stability. So we're going to go into stability, focus up here at the top. Now, it gives us a solution, a quiescent solution for the parameters in power flow. And so that's what's illustrated here. And so these are the real and reactive power, and we can see I have reactive current in my capacitors. So what I want to do is open up this breaker and resolve. And now I want to close the breaker and see what happens as far as voltage and current around this particular bus, because this could be connected to many other loads in my system. So now as I click on this breaker, the tool knows that I'm looking for, I didn't want to do that. I want to open and close it. Let's try this again. I want to close this breaker to start the motor. And what we have is I'm looking at the legend here. We're seeing the voltage and well, I'm not seeing the result I'm looking for. me go back and look at the database edit. Under stability, everything looks good. All right, so in stability, what it's showing me, and I can do the same thing by doing an individual motor. Let's kind of do it that way. Let's close, resolve, and open this switch and resolve it. Now, by bringing this motor online, we're seeing the bus voltage, the current, the real power, and the imaginary power or the reactive power. Well, that was the other thing I wanted to look at even in power flow, is that my bus in normal operations drops to less than 88% voltage. Oh, my breaker's picking up. That's what the problem is. So let's go back to database edit. I didn't want this breaker to trip. Okay, let's see if it'll do it now. Yeah, so I had, in my database edit, I had set this up with a specific value, and I don't want to do that. I just want to, because that's part of the problem. Let's just put a switch in there so I can turn it on and off. Let's go back to, so back in power flow, what I was trying to illustrate is when I solve this in normal operations, I have a 0.992 because of my power factor correction. My voltage is brought up. If I do an impact motor start to these loads, we can get there, hang in there with me. I want to do the same thing here. So in the process of starting these motors, my voltage on this bus drops to 0.08 per unit, which could be significant on the rest of my system. So I'm going to go back to database edit. We're not going to make these changes. We still have my, okay, so I'm going to close and resolve. I'm going to open and resolve this one. And the reason I wasn't getting the results that I expected was I had a breaker in here that tripped on the overcurrent. So now I'm going to close this switch and see what happens on my bus. And this is what I expected to see. Now what it's showing us is at the time the switch is closed, and we're looking here at the voltage on the top trace, it drops to a 0.82 and then lasts for about a half a second and then gradually gets back up to 0.97, whereas my current through that switch jumps up and then for some period of time stays in the ramp up mode. And here we can see the real power flow and the reactive power flow. So we could plot that along with the torque on the different motors. But the point is, how do we keep this voltage from occurring in our system? And the answer to that is using soft start. And so what I want to do is tune the soft start for something that will be less dramatic when I start these two motors. So I'm going to go back to my database edit. Let's not save anything. And I want to adjust those parameters in the motor model for stability. And as I go down here, let's say for the soft start 1, we're going to set up at 25% power for 2 seconds. And then we'll go to 50% power for 2 seconds. And then we'll go to 100% power, and we'll save that. And then on the second motor, so we want to stagger them just to see if it'll help the system that way. In this motor, I want to go to, let's say, 45% power for 3 seconds, and then 75% power for 3 seconds. Now again, what I'm trying to illustrate is the value of a what if, and for large companies that have these kind of situations, just starting up the motor could bring down the rest of the plant. And so this way it gives you the ability to tune on a what if basis. So let's go back to our stability. All right, so here we have this motor off, so I'm going to close and resolve. Both motors are running, and I want to open and resolve here. All right, so now we're going to start both motors with different profiles, staggered profiles, to see how low the voltage drops. And as I do that, we can see the voltage drops to 0.92, which certainly is much better than what we had. And you can see the staggered profile of both of the motors coming up and then gradually getting up to speed. But we've eliminated a lot of the problems we were seeing with the voltage, and it may take a little bit more tweaking on maybe staggering the start a little bit more. But at this point now, I feel more confident that less of my system is in jeopardy of going down as I start those two motors. Now, so what have we learned? Basically, in the database edit, we need to set up, to do a stability analysis, we need to set up the full flux model on the stability tab. So we go to stability, we can bring in generic values, and this will simulate a generic 500 horsepower. So whatever it is will have some reasonable profile. Now, if I have a need to use something more specific, there are built into the library a whole host of standard profiles from a couple other manufacturers, and it may be worthwhile to pick up the a more closely related RPM and horsepower rating versus what my system is showing. We also need to set up the motor load profile. Again, these can be based upon basically a profile, a mathematical equation or a profile that we can adjust, and for both starting and running. And then once we're there, then it's just a matter of going into stability and then understanding what it is that we're trying to analyze. In this case, I wanted to analyze what happens when I close that breaker. So for my one line, I had to open and resolve. It's a lot less dramatic when I open up the breaker, which you can see there's some reaction, but that's really not what I'm. In fact, you can see the difference over here on my legend. I go from 0.99 to 0.966 by taking that system offline. Okay, well, that covered what I wanted to do. Certainly, you're welcome to send any questions in. I probably don't have time to answer them now unless I could got a real quick. Oh, so it looks like we're in good shape as far as the presentation. Thank you for attending today, and we'll talk to you down the road. Have a good webinar Thursday this week as well. So please check back in with us, and we'll talk to you down the road. Stay safe.